I'm excited to present my work on the design and simulation of a MEMS thermal sensor using Simulink. The MEMS thermal sensor specifically detects changes in the temperature and converts these changes into electrical signals that we can measure and analyze. Our design relies on the principle that the resistance of the sensor material changes as the temperature varies. By incorporating the sensor as part of the voltage divider circuit, we can observe how the voltage output shifts with the temperature changes. For this simulation, I have modeled the sensor behavior by taking temperature inputs in Kelvin, processing them through the circuit, and analyzing the resulting voltage signal. The ultimate goal is to demonstrate how the system responds dynamically in variation of temperature. Now, let's explore how I set up the system in Simulink.
Hello everyone, in this video I'll be explaining the circuits we have used for our assignment. This circuit demonstrates the thermal sensor for MEMS application. I'll walk you through the components used and how they work together to achieve the system's purpose. So we start off with the constant block, which provides an input temperature, for example 323.15 Kelvin, which is about 58 degrees Celsius. This represents the external heat source in the system. Next we have the add block, which combines the input temperature of other signals such as feedback to calculate any errors. This system is crucial for temperature regulation. The control temperature source block is responsible for maintaining specific temperature in the system depending on the input conditions. This is a key element in simulating heat generation or dissipation. Next, we use the conductive heat transfer block, which models heat conduction. It has an area of 1 times 10 to the power of minus 4 squared meter squared, a thickness of 0.1 meters, and a thermal conductivity of 401 watts per Kelvin meter. The thermal mass block has a mass of 1 kilogram and a specific heat of 447 joules per Kelvin kilogram. This mass block represents an object being heated. This models how the material stores and releases heat. The thermistor is the core sensor in the circuit. It has a nominal resistance of 600 ohms, a characteristic temperature of 500 Kelvin, and a reference temperature of 298.15 Kelvin. The thermistor converts the temperature changes into resistance changes, allowing us to measure temperature. We make use of a 300 ohm resistor to complete the circuit and also voltage sensors to measure the voltage across the thermistor, which provides data for the temperature calculations. Finally, the display blocks show the output data such as the voltage and temperature values. These results allow us to verify the system's performance. The circuit efficiently simulates the thermal sensors for MEMS application. Each component work together to model the heat conduction, thermal storage, and temperature measurement.
Hi, my name is Ibrahim and I'm going to be talking about the simulation output. So we will be using three main temperatures. So one is going to be 273.15. This is in Kelvin. So we'll use this. We'll use 298.15, which is 25 degrees Celsius, and 323.15, which is 50. So if we compare it in degrees Celsius, it's going to be 0, 25, and 50. So after running the simulation for 273.15, which is 0 degrees, our thermistor value was 27.94. And if we change this to 298.15, our value is going to look like this, 26.61, which is a decrease from the previous value of our thermistor. As we increase the temperature again over here to 50 degrees Celsius, it's 25.13. So this is showing that there is a change as the temperature rises, the voltage across the thermistor reduces. So what do we figure out from the simulation? From the simulation, when the voltage across the thermistor increases, indicating that the sensor reacts inversely to temperature changes, this behavior highlights negative temperature coefficient of the thermistor. So when we increased it to 50, as expected, the voltage across the thermistor decreased even further since it's inversely proportional. This demonstrates that the thermistor sensitivity to temperature variation is accurate. So what are some findings from our simulation? The output voltage behavior. The voltage across the thermistor decreases as temperature increases. This is predictable, and linear behavior confirms that the thermistor is negative temperature coefficient. And sensor sensitivity. The design of the voltage divider circuit isolates the thermistor temperature dependent resistance. This ensures the system is sensitive enough to detect even small changes, making it suitable for precise monitoring. And my groupmate will talk about some practical uses.
To conclude this simulation shows that the MEMS thermal sensor can measure temperature changes by turning them into voltage signal. The result confirms that the sensor is reliable and works well. This type of sensor is very useful as in many areas, such as the first one is factories. It helps to control the machines and process where the right temperature is important, like in making it chemical or electronics. In hospital, for the other example, in hospitals, it can be used for incubators for babies or to check the temperature in medical machines.